Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New St. Augustine.
On the 4th of July 1989, I experimentally discovered that when 64 binary thousand processors are communicating together and are computing together as one seamless, cohesive supercomputer, then my 65,536 processors became as bright as the sun. I was in the news headlines because I brought a new face, a new voice, and a new vision to the story of the development of the modern supercomputer that is not a computer per se, but that is a new internet de facto. The lone wolf inventor of a new internet must invent every node of his new internet. A new internet could only be invented by a cross-disciplinary inventor that commanded a broad overview of the frontiers of mathematics, of the frontiers of physics, and of the frontiers of computer science. That inventor of a new internet must have the intellectual maturity needed to bring together discoveries and inventions from disparate fields, such as modern calculus, extreme scale algebra, and massively parallel processing. That inventor of a new internet must bring together highly specialized knowledge that were previously siloed. I invented a second new internet that I called a cosmic ball. In the mid-1970s, my new internet remained science fiction. But on the 4th of July 1989, I constructively reduced that hyperbole science fiction to non-fiction, and I did so when I became the first person to experimentally discover that an ensemble of the slowest 65,536 processors in the world can be harnessed to compute faster than the fastest supercomputer in the world and compute faster while solving the toughest problems arising in extreme scale computational physics. I was in the news onward of the 4th of July 1989 because I experimentally discovered how to reduce the performance abyss between the sequential or the vector processing supercomputer and the massively parallel processing supercomputer. I did not experimentally discover the technology of the massively parallel processing supercomputer and invented that technology by inventing how to tweak the sequential processing codes that arose in extreme scale computational mathematics. Nor did I constructively reduce to practice or experimentally invent the new tech supercomputer, and did so by inventing how to vectorize the vector processing codes that arose in extreme scale computational physics. I invented the parallel processing supercomputer from first principles and invented that supercomputer from the laws of classical physics and invented that supercomputer from the partial differential equations of modern calculus that encoded those laws and invented that supercomputer from the partial difference equations of extreme scale algebra that approximated those partial differential equations. In the early 1980s, I invented 9 partial differential equations of modern calculus that fit the second law of motion of physics, rather than invent a law of motion of physics that fit the partial differential equations on the mathematician's blackboard and in the calculus textbook. Mathematics is not a science in its own right. The new calculus that I invented, namely the 9th system of partial differential equations called Philip Emeagwali's equations, is the middle science that mediates between the mind of man and the motion of objects. It is that intermediary position of my new calculus that prompted the debate on whether my new mathematics is discovered or invented and patentable. I see the 9 Philip Emeagwali's equations as inventions that were abstracted from the discovery of the second law of motion of physics that occurred 330 years ago. The physical law that I encoded into Philip Emeagwali's equations existed 13.82 billion years ago when the universe was born from the Big Bang explosion. But the mathematical terms that codified those laws could have been known 13.82 billion years ago, but were not known then. The 9 new partial differential equations that I invented were beings of reason, but what they simulated were real beings. The reason I make this distinction between beings of reason and real beings is because I am often asked, did you discover or invent the Philip Emeagwali's equations? My answer is that I discovered the Philip Emeagwali's equations. If my partial differential equations existed in textbooks of modern calculus and that I invented the Philip Emeagwali's equations, if my partial differential equations did not previously exist in calculus textbooks. For instance, we discovered Mount Kilimanjaro because it pre-existed. But we invented the massively parallel processing supercomputer on the 4th of July 1989 because it did not pre-exist. In computational physics, extreme scale algebra is the recurring decimal and the elephant in the room. Algebra that arose from discretizing the partial differential equation is the way the supercomputer experienced calculus. Those experimental discoveries of how to massively parallel process across a new internet, that is a new global network of processors, enabled me to forge my path to the farthest frontier of supercomputing, that is the modern supercomputer. What made the news headlines in 1989 was that I invented the technology of the massively parallel processing supercomputer, and that I constructively reduced that technology to practice. And I did so on the 4th of July 1989. And I did so when supercomputer textbooks considered parallel computing, many things at once, to be impossible. And I did so in 1989 when all the 25,000 vector processing supercomputer scientists in the world considered it to be impossible to parallel process the most extreme scale problems arising in computational physics, such as general circulation modeling, to foresee otherwise unforeseeable climate changes. The June 14, 1976 issue of the Computer World magazine reported on a special session on parallel processing that was held at the National Computer Conference in New York City. The Computer World magazine reported that a panelist of supercomputer experts at the 1976 National Computer Conference were of the opinion that, I quote, "Those machines often turn out to be large and clumsy, and several of the large parallel processor designs since then have failed. Now we are moving into the modern era." End of quote. When I began supercomputing in 1974, massively parallel processing supercomputer coding was like rubbing rocks until they caught fire. Sometimes it is difficult to translate thoughts from one medium to another. The article is written to be read on a page, but the algorithm is invented to be coded on a processor. For the 16 years onward of June 20, 1974, every supercomputer scientist seemed to be writing articles while I was coding supercomputers day and night, and trying to explain my abstract supercomputer algorithms to the layperson or to the vector processing supercomputer scientist is like trying to rub rocks until they catch fire. I began supercomputing 18 months after the last man walked on the moon. On June 20, 1974, the day I began sequential processing supercomputing, it was easier to travel to the moon than to travel to the frontier of the massively parallel processing supercomputer that is the precursor to the modern supercomputer. In the 1970s and 80s, to parallel process across a new internet that was a new global network of 64 binary thousand commodity off-the-shelf processors was like walking alone through a dark rainforest, and doing so alone with only a dim lamp. My quest for the massively parallel processing supercomputer was my attempt to discover that the impossible to compute is in fact possible to compute. Parallel processing is the technique of fastest supercomputing that is fastest by computing many things at once or in parallel instead of computing only one thing at a time or in sequence. To the supercomputer scientists of 1989 and earlier, To invent the parallel processing supercomputer was to experimentally discover that massively parallel processing the toughest problems arising in extreme scale computational physics is not a waste of time. I was in the news in 1989 because I figured out how to save time and how to do so by reducing 65,536 days or 108 years of time to solution on one processor that is not a member of an ensemble of processors, and reducing that time to solution to only 1 day of time to solution across an ensemble of 65,536 tightly coupled processors that were the building blocks of a new internet that was a new supercomputer and a new computer. My experimental discovery was recognized in the June 20, 1990 issue of the Wall Street Journal. The Wall Street Journal reported that my experimental discovery of the massively parallel processing supercomputer will change the way we look at the supercomputer. In the old way, we thought about a conventional supercomputer as powered by one strong ox. That strong ox was my metaphor for one powerful processor. In my new way, I thought about a modern supercomputer as powered by 65,536 chickens. Those chickens were my metaphors for my 65,536 weak processors. I theorized that the grand challenge problems of our children's children will be solved by 1 billion grasshoppers. Each grasshopper was a metaphor for a computer on the internet of the future.
Insightful and brilliant lecture.